Computers execute repetitive tasks with high precision, but repetition requires boundaries. Without a defined stop condition, an unchecked loop consumes system resources until it fails. Successful loop construction depends on a developer's ability to translate abstract human logic into the concrete mathematical boundaries a machine requires. To perform this translation, we divide loops into two architectural categories. The first is definite iteration. Developers use a definite loop when the exact size of the dataset or the required number of steps is known before the execution begins. The sequence length is fixed. And the second category is indefinite iteration. Here, the stop point is unknown. The loop relies on a Boolean condition, running continuously until it encounters a specific future event or data trigger. Choosing between a definite or indefinite loop dictates how the program allocates memory and manages data state over time. We can apply this translation process to a standard programming requirement, summing all the valid game scores in a dataset. Before writing loop syntax, developers must isolate the specific data that needs to be tracked across the entire lifecycle of the operation. In computer science, we track a running total using the Accumulator Pattern. Accumulators are governed by the rules of scope. The variable holding the total must be initialized outside the loop structure before the repetition begins. As the active loop processes each game score, the new data is passed outward to update this protected accumulator. Failing to isolate this storage from the repetition mechanism causes the program to overwrite its own memory, resetting the running total on every rotation. With the memory isolated, we can construct a definite loop using a for statement. A for loop provides a safety mechanism because the iterator variable tracking the current position updates itself automatically. This diagram illustrates the range function, the engine for generating integer sequences. It accepts three parameters: start, stop, and step. The most critical rule is the exclusive stop bound. The sequence will execute up to, but will never include the defined stop value. When using a negative step to count backward, the starting number must be strictly greater than the stopping number. If you provide an invalid bound, such as starting at 3 and stepping backward toward 52, Python resolves to an empty sequence, so the loop never begins. This silent skipping can be difficult to debug, as the program continues running without a formal crash report. Definite loops provide baseline safety because the sequence boundaries and pointers are pre-calculated before execution. When the stop condition is dynamic, we must use a while loop. Since the number of steps is not pre-calculated, while loops require a strict architectural blueprint to ensure they eventually terminate. We call this the ICU framework: initialize, control, update. First is initialize, capturing user input before the loop starts. Second is control, the Boolean gatekeeper executing while true. Q is the sentinel value, forcing it to false. Finally, update. The program requests new input inside the loop on every cycle. Indefinite loops offer the flexibility to handle dynamic stop conditions, but they require strict architectural compliance to the ICU framework. Omitting any of these three components results in logic that cannot terminate. When that architectural compliance fails, the translation between logic and machine code breaks down. This diagram shows the off by 1 error. Adding 1 to a range bound to force a stop value inclusion makes the pointer access a non-existent memory slot, triggering an index error. A missing update step creates a different failure. Without a way to modify the control variable, the Boolean gatekeeper never receives new data. The loop remains in its initial state, executing endlessly and freezing the program. The final failure point is the scope trap, occurring when the accumulator is incorrectly initialized inside the loop. Trapped in local scope, the accumulator reinitializes on every rotation. Your data resets to 0 on every pass. Silent logic failures and program freezes generally indicate a violation of loop anatomy or memory scope, rather than simple syntax typos. Once you master sequence boundaries and the ICU framework, Python offers powerful structural ways to compress your logic. For definite iteration, the most efficient optimization is the list comprehension. As shown here, a standard 3-line for loop designed to modify elements in an array can be translated into a single line of code. This abstraction reduces code bloat and allows the Python interpreter to execute the logic more efficiently. Beneath the concise syntax, the underlying mechanics remain the same. The sequence still requires a defined start, an exclusive stop bound, and an automatic update. Mastery of iteration involves defining rigorous mathematical boundaries, isolating memory scope, and intelligently tracking state, regardless of the final code length. Once you master sequence boundaries and the ICU framework, Python offers structural ways to compress your logic. For definite iteration, the most efficient optimization is the list comprehension. As shown here, a standard 3-line for loop designed to modify elements in an array can be translated into a single line of code. This abstraction reduces code bloat and allows the Python interpreter to execute the logic more efficiently. Beneath the concise syntax, the underlying mechanics remain the same. The sequence still requires a defined start, an exclusive stop bound, and an automatic update. Mastery of iteration involves defining rigorous mathematical boundaries, isolating memory scope, and intelligently tracking state, regardless of the final code length.